Hello, this is Philip Myers of PEMY Consulting. Welcome to Strength of Materials, Unit 2. In this module, we'll learn about the two basic components of stress, normal stress and shearing stress. We will learn the meaning of the terms uniaxial, biaxial, and triaxial stress. We will also learn what a stress state is and how it is affected by your perspective, meaning which direction you slice the solid to understand its stress state. In essence, we will build on the stress cube concept we talked about in an earlier video. The post-tensile specimen has a cup and cone rupture right here, in addition to the necking, which is the drastic thinning of the cross-section here. We learned in a previous module that steel starts out with a range that is elastic. If you remove the force pulling on the specimen, it would return to its original shape. But if you keep pulling, the yield point is reached beyond which, with increasing force, there is increasing permanent set or elongation. Note that the elongation around the 20% mark for carbon steel is well illustrated by this pre- and post-test specimen. Strain hardening occurs as the elongation continues until the ultimate strength is reached. Beyond this point, the area of the bar rapidly decreases, and there is a decrease in the force required to thin the bar until it finally fractures. The tensile test generates what is called a uniaxial stress. The bar is prismatic, meaning that its cross-section does not change across the length of the bar. However, in the case of the tensile test, the ends are beefed up to make sure that the ends don't fail. A uniaxial stress occurs when a force is applied along the axis as shown here and through the bar's centroid. Now let's take a free body diagram cut here. Note that the cut is normal or perpendicular to the bar's axis. If we look at the bar cross section here, we can see that the force is also normal to that cut plane, which is called the x-plane, since it's normal to the x-axis. Let's look at normal stress in more detail. In order for the bar to remain in one piece, there must be an internal normal force as identified here. Where the bar is fairly long and the resultant force is pulling through the centroid, we can see that the average stresses will be approximately uniform across the cut plane. In this way, we are able to say that stress is force divided by area, but recognize that it is an average of the actual stresses, which can vary from point to point. It's also useful to know that any small stress cube extracted from within the bar will behave just as described for the larger bar. It's often the case that forces act in more than one direction at once. A classic example is a pipe or a pressure vessel. These have stresses which go around the girth and are called hoop stresses, but there is also a stress that is longitudinal with a pipe or a vessel. The plate used to construct this equipment is subject to biaxial stresses. Finally, the most complex of the stress conditions, which act in three directions simultaneously, are called the triaxial stress state. Usually, finite element analysis is needed to supplement understanding of the actual stresses and directions associated with the complexities of the involved geometries. We previously discussed normal stresses. The second stress type we now discuss is shear stress. The best way to think of shear stress is illustrated by a deck of cards. While no tension or compression is applied to the deck, a push from the side will shear the deck. This is also illustrated by the arrows here. Finally, a real example of shear stress might be the joining of tank plates in a bolted or riveted tank. This force acting in this direction and this direction simultaneously tend to cause shear across the plane here. The formula for shear stress is given by force per unit area Of course, the area is the area of the bolt, so it's pi r squared. If we relate it to diameter instead, the formula becomes tau equals 4f divided by pi d squared. Comparing the first two bullets is comparing scalars to vectors. A scalar is just a real number, so temperature is a scalar. Speed is also just a number or a scalar, but if we couple that or associate it with a direction, then we have a vector. And a vector, as you recall, has both magnitude and direction. Forces can be considered as vectors. Although linear algebra allows for any number of dimensions in engineering, we typically work in 3 dimensions, so vectors would have 1, 2, or 3 components, one for each of the dimensions we're working with. In this figure, we have a 2-dimensional vector. Let's assume that it's a force. You recall from your previous work that the y component and the x component can easily be found by trigonometry. In 3 dimensions, we do the same thing with any 2 dimensions and do it twice. So for example, we first get the projection of the vector on the z-axis and the projection onto the xy plane. Finally, we can use trigonometry to resolve the projection in the xy plane into the x-coordinate and the y-coordinate. Therefore, we end up with the 3 components of this 3-dimensional force. Consider the face of the stress cube, which I have reoriented this way. Taking the ideas just discussed about vectors, we see that any arbitrary force acting on the z face of the stress cube can always be resolved into 1 normal force in the z direction and 2 shearing stresses in the z plane. The 2 components that are within the plane are the shearing stresses, and the one that's normal to the plane is the normal stress. You can see that when we do this for the 3 planes, we end up with the 9 stress components that we talked about earlier. So far, we have taken the free body diagram cut plane normal to the force acting in the axial direction of the rod. But we can take a cut plane at any angle we choose, for example, this plane, which is at this angle, to the axis. Now something very strange emerges. With respect to this new plane, there is now not only a normal stress, but a shearing stress as well, indicated by decomposing the axial force, the uniaxial force, into its directional components along the new coordinate system axis. The idea is that a stress state is a matter of what plane you are looking at, and so there are obviously an infinite number of stress states for the stress cube, since you can orient the stress cube in an infinite number of ways. We will develop a complete understanding of this concept when we get to the concept of the Mohr circle, but this introduces the idea of a stress state. Next time we will talk about the number of stress states, how they are represented, and how the basic laws of statics apply to stress elements, and what the results are. In this module, we have learned more terminology, namely uniaxial, biaxial, and triaxial stresses. We covered the 2 basic stress components, normal stresses and shearing stresses. We learned that these stresses depend on the orientation of the stress element, and that the stress state is a matter of perspective, or how we are selecting the stress element orientation within the solid. Thank you.